All right. In this video, I'm going to show you how to put a radio observation into Skynet. There are different types of radio observations you could do with Skynet: a timing observation, a spectrum, or a map. And in this video, I'm going to show you how to do a mapping observation. We're going to map a source, and in a later video, we'll turn it into an image. We'll make the invisible sky visible, see what the human eye cannot. And we're doing this in support of Module 1B or Module 1C. I'm just going to shoot one video that can work for either module. But let me take a minute to explain the goals of the two modules. In Module 1B, we're looking at the moon. We're going to look at the moon at two different phases. And here we're looking at a moon calendar. You can see today when I'm shooting this video, it's the 23rd, pretty close to a full phase, as much light as we're going to get. And then we'll map it again once the phase has changed a lot. Now, sometimes, like if today was the 18th, like a quarter moon, I don't have to wait a few days to map again at a sufficiently different phase. Since we're approaching full moon, you can see it's many days of near maximum brightness. So I'm going to have to wait about a week for the phase to change enough for me to map it again. Because what I'm trying to figure out, yes, the brightness of the moon changes at visible wavelengths because we're reflecting different amounts of sunlight. But does the brightness of the moon change at radio wavelengths? If it does, and by the same amount, we're also reflecting sunlight. But if it doesn't, if it's constant, then we're not detecting reflected light at all. We're detecting emitted light, emitted radio waves. And this would be from deep enough down in the lunar soil where the temperature is approximately constant. Just like on Earth, if you go down into caves, the temperature is pretty constant there throughout the day, throughout all the seasons. It's always the same temperature. And if that's what we find with the moon, we can measure the temperature of the moon all the way from here. So that's the goal of 1B. 1C, we're going to learn similar skills. We'll also do temperature calculations, but the target's different. The target in this case in 1C is Jupiter. Much, much fainter source, but we should be able to detect it. And detect it, measure its brightness, measure its temperature, then ask ourselves, is that reasonable given its distance from the sun, the temperature that we get? If it's not reasonable, it's much, much higher, then what we're detecting is not thermal emission, but something else. And so either we'll measure the temperature of Jupiter, or we're learning about some new, more powerful emission mechanism. Those are the goals. Now, whenever you put an observation in of a source, and if you want to measure its brightness, you need to also, right around the same time, measure a calibration source, a source of known brightness. Like we can map the moon, we can map Jupiter, get an image and measure how bright it is, but the units are arbitrary. And the system changes slowly with time. So right around the same time, we want to map a source of known brightness. And then we compare the two, and we can get the brightness of the moon or the brightness of Jupiter into standard units that we can use to calculate temperatures. So for each of these observations, either the first moon observation or the second moon observation or the Jupiter observation, we will also be mapping a calibration source. And there are three that we use to calibrate the bright radio sky. There's Cygnus A, which is a galaxy, bright at radio wavelengths. There's Taurus A, also known as the Crab Nebula, a supernova remnant. And there's Virgo A, Its technical name is 3C274. And they're distributed kind of evenly around the sky. So whatever your target is, you're going to pick the nearest calibration source and hit them both. And you have to do some planning, whether it's the moon or Jupiter. So the first thing you want to do this planning is you go to Skynet, you go to My Observatory, go down to Radio Observing, and let's add a new observation. Before we do anything, let's just play with the sky viewer, find out where our targets are. So hit the little clock for the current time. And here I see the moon. It's close to the crab. There's one of our calibration sources. And, I said we'll have to observe it now and observe it a little bit later, either a few days later, or where I'm at now, I'm actually going to have to go about a whole week to get a difference in phase. So let me switch this to, it's already in days. I'm going to go forward 1, 2, 3, 4, 5, 6, 7. So that gets me over here near this calibration source, maybe even 8. Now I'm off the map. Let me switch to hours and advance it. You can see it there. You want to use the same calibration source for both moon measurements. So I'm going to go with Virgo A, 3C274 as my calibration source. Now, if I'm doing Jupiter, it's over here. And it's kind of close to the crab. Now, and so I'll use the crab as the calibration source. Now, in the future, Jupiter will be in a different part of the sky. The moon will be in a different part of the sky. So you have to play with this map, find Jupiter, find the moon, find where the moon will be for both of your observations, pick one calibration source for the moon, pick an appropriate calibration source for Jupiter. You have to pick that stuff yourself. Your instructor will help you. Okay, let's start with moon observations. I'm going to show you how to set them all up on this page here. So keyword moon, search. Okay, it found the moon. There it is marked. I'll put it back on today. There it is. And here's the current coordinates, and we'll update the coordinates when this is dispatched. And this one I want to go right away. So I would set it like this. You can see the air mass chart. It's observable right now, observable for a long period of time. The observability chart, sometimes called an air mass chart. So that's good. And you always want to put in your calibration source. So you'd go ahead and submit this observation. And while you're doing that, maybe a teammate does the calibration source. And for the moon, I said in this case, it's moving over towards Virgo. So I'll type in Vir A, search, and it found it here, 3C274. Okay, has its coordinates. That's fine. You can observe it right away. Now, you also want to put in a moon observation days later. So we're thinking, in this case, 1, 2, 3, 4, 5, 6, 7 days or so. This is around the 30th. You can see that here on the moon phase chart around the 30th, maybe even the 31st. I'll put in the 30th though. And let's see, let's start with the moon. Maybe I'd call this one moon delayed. Now delay the start of the observation until, let's say, the 30th. That's how you put in a delayed observation. And again, it needs a calibration source, so you'd also do it with Virgo. Oops, Virgo A, search. Found it. And so it also will be submitted with the delay. And so there's 4 observations there. If you have 4 people on your team, each one does a different one. The Jupiter team, let's take a look at that one. One person on the team will search on Jupiter. There it is. And don't need to delay that. You can, if you're trying to get it out of the way of those moon observations. Some people in the class might be doing the moon observation. Some people will be doing the Jupiter observation. So maybe I do want to delay it a little bit. Moon observations can go one night, and then the Jupiter observations, and then, later on, the other moon observation. Okay, so up to you. But the other thing with Jupiter being so faint, you want to click here, observe only if the sun is under the horizon. As I mentioned in a previous video, you could do radio astronomy during the day, but if you're observing something faint, it can get messed up by the sun not scattering radio waves all through the sky. That doesn't happen. The sky remains dark, but sometimes those radio waves from the sun can bounce off these struts and get in the receiver at a very low level, but it can mess up faint observations. Most likely, it's not going to happen for Jupiter. You can observe Jupiter during the day. Most of the time, it comes out just fine. But if it happens to be in the wrong part of the sky, such that the angles all line up perfectly, it can get messed up. So with Jupiter, if you want to be safe, you can mark observe only if the sun is under the horizon. Okay. And then it needs its counterpart. Its counterpart was the crab calibration observations. So maybe one person puts in Jupiter, another one, the crab's pretty close, we put in the crab. That one you can observe day or night. It's bright. So those are the 6 basic observations. If you have 4 people on your team, that means 2 people on the Jupiter team didn't get to do anything. So they can also put in another Jupiter observation and another crab observation. Maybe you delay those a little bit longer. And so, they stay out of each other's way. Okay, a lot of discussion there, but I'm just setting up all the different possibilities. It's nice to make a table. So here's a table I made for my students. Now, of course, this table only holds for this time of year. This was our observing plan. The moon and Virgo delayed, Jupiter and Taurus delayed, and Jupiter checked to observe when the sun's down. Each semester, you'll have to look at the sky and come up with your own observing plan. Okay. Let's continue. I'll put in this crab observation here with the delay. Save and continue. The next page is the receiver settings page. This is analogous to the filters page on the optical side of Skynet. This is where you would pick your filter. I want to look at red light. I want to look at green light. Except in the radio, you don't have like a piece of glass that you hold under the receiver. It doesn't work that way. Instead, you're bringing in a spectrum electronically, and you can filter it electronically. So we want to be in low resolution mode. High resolution is good for spectra and things, but low resolution mode. And the receiver works all the way from 1300 to 1800 megahertz in frequency. Well, about 1350 to 1750. But we don't want to take that entire spectrum. We have a filter here running from 1355 to 1435. So only 80 megahertz instead of 400 to 500 megahertz. And these 80 megahertz are centered on 1395. And we want to run with this filter. Here's the reason why. Here's the full spectrum from 1350 to 1750. And these slow little wiggles, that's just part of the instrument, the electronics of the instrument, how it responds. You get these undulations. That's okay. Nothing you can do about that. What we're worried about are these giant spikes over here at particular frequencies. This is what we call radio frequency interference, RFI. This is created by civilization, transmitters, satellites, all sorts of things. We want to avoid this. I mentioned in a previous video, the signals that we're detecting from deep space are incredibly weak, and they can easily be overpowered by radio signals here on Earth. Over here, here's that H1 passband from 1355 to 1435. It's a protected band. No one's supposed to be transmitting in there, although often people do. But here people are always transmitting. So we're going to use this region here. You see little spikes, like that little spike there is probably RFI. This little spike here, that is the hydrogen emission line. That's an astronomical emission line. So that we want quite often. Okay. So this is like putting that piece of glass in front of the detector, except it's done electronically after the fact. It's an electronic filter. You do not want to be in pulsar mode. Even later in the course, when we study pulsars, we're not going to be in pulsar mode. Channels can be 1024. Okay, save and continue. Now, pick a time account if you have multiple. Path type. There are all sorts of different ways we can track our source. Some of it's for timing and spectroscopy. We're going to go to map. We're going to make a raster map. And it's a little bit more flexible than optical. You know, your optical telescope has a camera, has a detector in there, and the size of the detector is fixed. The size of your image is fixed in an optical telescope. But here with the radio telescope, since we're taking one pixel, moving it around, we can move it around over whatever size we want. So step one is picking the size of the map. See, we have two options, beams and degrees. For mapping a source, we're normally going to be in beams. Bring the images back up. So here's a source we looked at in a previous video. The source here in the middle, that's the Eagle Nebula. It's a radio source. But it's a blob because, again, at the radio, everything is blurred. Imagine taking a cross section across that source. Looks something like this. Brightest in the middle, fainter in the wings. The amount of blurring, we call that the beam. So if you go about halfway down from the max, the full width at half max, that scale is what we call the beam, pretty close to full width at half max. Here's 1 sigma, 68.3% of the radio waves. The brightness is contained within there, at least for this cross section. 2 sigma, it's about 95%, 3 sigma, 99.7%. So you got to go about 3 sigma out and you have the whole source all the way through the wings. But 3 beams isn't enough because we also need some background around our source. So we want our source going out to 3 sigmas about here, but we want to go a little bit farther. We have a good background so we can measure how bright the source is above the background. So we typically go out to 6 beams. So let's make our map 6 beams by 6 beams. You don't want to ever go any smaller than that. And it will convert it into degrees. And you may notice it's a different amount of degrees in right ascension and declination. It's more in right ascension. This is a subtlety, but let me explain it to you. So here's the celestial sphere. We got lines of declination, lines of right ascension. And just like on the globe, where the lines of constant longitude, they converge as you get up to the North Pole. Just like on the sky, the lines of right ascension are converging as you get to the North Celestial Pole. So let's say we're looking at a region down here at the equator from here to here. That's about 15 degrees over which I'm moving my mouse. If I move the mouse over the same distance up here, that's about 30 degrees. The same distance up here, that's about 60 degrees. Because the lines are getting closer together, you're covering more in right ascension. Same amount of degrees on the sky, but it's more in the right ascension coordinate system because the coordinate system is converging. It's a technicality. I just wanted to explain why these numbers differ. So anyway, we've chosen the size of our map. Now, the raster. We're going to raster around in this region. And do we want to raster in right ascension or raster in declination? Here's a raster in right ascension. We go in right ascension, then increment in declination, and then back in right ascension, increment, and so forth. This is a right ascension raster. And here's a declination raster where you go up and down, up and down, up and down, and over as you go. Doesn't really matter. I normally go in right ascension because for many geometries of the telescope, you're not moving the dish as much up and down against gravity as left and right. It's less wear and tear on the gears and the motors if you don't move the telescope up and down against gravity. Right ascension is not perfectly aligned, perpendicular to the gravitational direction, but often it's better than moving in declination. Now, we pick the pattern. What is the spacing? So we picked a left-right, right ascension raster. What's the spacing between sweeps? And how often will I read along the sweep? So there's a rule. You need to sample every 0.4 beams. If you want to reconstruct the image, all you need is a sampling every 0.4 beams to reconstruct it. Except when we tell the telescope to do this raster pattern, it won't do it perfectly. It's windy, it'll be blown around a bit. It has a hard time navigating the turnarounds, so sometimes it gets a little messy out there, and you can get gaps bigger than whatever you pick. So let's be conservative. Instead of 0.4 beams, let's go with 0.2 beams. That's 1/5 of a beam. So the gap between the sweeps, let's make that 1/5 of a beam. And the gap along the sweeps, we read every 1/5 of a beam. Keep it the same. Okay. Last thing we need is, you can look at it two ways. If I'm collecting data along the sweeps, every 1/5 of a beam, how long do I want to collect data there? Now, the telescope's not going to stop, collect, move, stop, collect, move, stop, collect. That's a lot of wear and tear on the mount. Instead, we're doing something called an on-the-fly mapping. We're collecting data and moving as we're collecting the data. So really, the integration time at any point, it's related to the slew speed. Between this measurement and this measurement, that's 1/5 of a beam. It's a certain number of degrees, fraction of a degree. And the time that you're integrating at any one point, since you're actually moving, it's the time it takes to move from this point to this. That's a speed. You move in a certain number of degrees per second. So you can pick an integration time or you can pick a slew speed. And we're going to go with slew speed because if you move the telescope too quick, bad things happen. So here's a raster map where we're moving 0.3 degrees per second. As I said, it sometimes has a tough time with the turnarounds. Imagine you're driving down the highway in your car, 60 miles an hour, and you just throw it into reverse to go in the backwards direction. That's going to be messy. And same thing here. You have this tremendous weight moving at a certain speed, and then they don't really even slow it down and stop it. They just move it the other way. So it jerks, and you have a poor pattern at the edges. That's okay, as long as it's good and consistent in the middle. Over here, we have 0.5 degrees per second. And here the messed up region gets bigger and it crosses the middle of the map, and we don't want that. That will mess up our reconstruction. It's not a big deal if we're making a big map and only the edges way out here get messed up and everything inside is good. But these are tiny maps. And so we got to make sure some of it's good. So we're going to go with a slew speed of 0.3 degrees per second. So slew speed, 0.3 degrees. Here it says this map's going to take 7.8 minutes. Takes a little bit of time. And each person in your group will submit a different one. So one person doesn't get the whole time hit. Save and continue. Again, a moon, a calibrator. A moon at a later date, calibrator at that same later date. And then the other team, Jupiter and a calibrator. And if the other team members want something to do, they can also put in Jupiter in the calibrator. Then you submit it. Okay. That is how we put in those radio observations for modules 1B and 1C.